In this video, we're going to go through a quick example of how to minimize the number of states in an automaton. We know that we can have equivalent DFAs that don't look the same. They can have different diagrams, they can have different transition tables. The only thing that we need for them to be the same, for them to be equivalent, is if they accept the same inputs. So two machines that accept the same type of input, that accept the same regular expression, are going to be called equivalent. And we can come up with lots of different machines that all accept the same regular expression. So among those machines that accept a particular regular expression, we can talk about some being more minimal than others. Some can have fewer states than others. And typically, if we're going to use these in application, it is to our advantage to have as few states as possible. This will save on hardware if we're going to implement this in a physical setting. This will save on the amount of software we have to write if we're going to implement it in a software setting. Here's an algorithm, and this is very mathematical, and this is hard to read. So I'm just going to go over it a little bit, and then we're going to go through a full example of how to minimize the number of states in a DFA. And there are a lot of ways to do this, and none of them are actually guaranteed to give you the absolute minimal representation for any DFA that you input. It doesn't work that way. But these are all techniques that will help you determine which states can be cut out of a DFA and which transitions can be rerouted to other states. So basically the idea is that we're going to partition the states. And we're going to start off with the partition of states. We're going to take every pair of states that are either final states or non-final states. So the states where, yes, we've accepted a thing, or the states where, no, we haven't accepted a thing. So we're just going to come up with all possible pairs of those. So you can imagine that if you know anything about combinatorics, if you've got a sufficiently large state machine here, and you're going to try to do this, this is going to be a lot of states. And then what we do is we keep refining this set. And we refine it by looking at, within each pair, we look at all transitions from those states. And we include it if the transitions are going to be the same, or if the transitions go to another set of states that is already in our set. And if one of these things is not true, well, if both of these things are not true, then we cut that state out of our next iteration, and then we don't have it anymore. And which means that those two states are not actually equivalent. So states are going to be considered equivalent if they transition to the same next state for the same inputs, basically. And what this rule is doing is trying to decide which states are not going to have that property, and it will cut them out. So this is all the possible states that could potentially be the same. And then now we're going to keep refining our set and cut out states that we know are not the same. So let's go through an example. You don't really understand this until you see an example. Here is a state machine. Here's a DFA, and here's its transition table. So what we're going to do is first look at all the states 0 through 4, and we're going to come up with this set E0. This is going to be all pairs of states that are either final or non-final sets. So 0 and 4 are non-final. Those are the only two non-final. And 1, 2, and 3, these are all final states because they have the two circles. These are the ones that indicate that the input has been accepted. So 1, 2, and 1, 3, and 2, 3. Remember, sets are, it doesn't matter what order we list the things, so you don't have the full possible number of permutations here. And then what we do is we refine it. We look at this set and we say, okay, 0 and 4. What happens when I get a B in 0 and 4? Well, both states end up in the state 4. So that's good, right? That's fine, because this means that on the B transition, I get the same state. That's not going to eject this set 0, 4 from my partition. However, look what happens when you get an A. When I get an A from set 0, I go to 1. When I get an A in state 4, I go to 4. So this means that when I'm in the partition 0, 4, and my input is an A, I go to the set 1, 4. But 1, 4 is not one of my potential states here. 1 and 4 cannot possibly be equivalent, because 1 is a final state and 4 is a non-final state. They have different outputs. So states with different outputs can't be the same. So therefore, we exclude the set 0, 4 from my next iteration of this process, because I now know that 0 and 4 cannot possibly be the same state. These states cannot be equivalent. I look at 1, 2, and I see that on B, they both go to the same state. That's fine. See, on this rule here. It says on the next state, if they're the same, then that's okay. Or if they both go to a pair that is already in the set, it's okay. So in this case, the 1 and 3, they the 1 and 2, on B they both go to 3, so it's the same. 3 as a singleton isn't one of our sets, but that's okay. It's the same thing. So 3, 3, that would be fine. On A, where do we go? On A, from 1 I go to 2, and on A from 2 I go to 3. So on A, from the set 1, 2, I go to the set 2, 3. And the set 2, 3 is in my partition, so that's fine. It's now possible for states 1 and 2 to be equivalent, because their next states are potentially the same state. Their next states are going to be 2 and 3, and those are possibly equivalent states. So we maintain this. Same thing with 1, 3, and 2, 3. Right? All of these end up on B going to 3, and end up on A, well, on 2, 3, they both go to 3 as well. So all 3 of these stay in the partition. And then you iterate this again, because every time you run this process, you cut some of these sets out. So it's possible that on this first run, some of these might have gone back to 0, 4. And you would have kept them in because 0, 4 is still in the partition. But now that 0, 4 has been kicked out of the partition, on this next iteration, you would then kick out that set that went to 0, 4, because it's now not going to a set of states that's in the partition. But in this case, we've already, 0, 4 is the only one we want to kick out. And when you go to the next state, E2 here, it's the same as the previous one. And you stop this process as soon as you get to a refinement of the partition that is equivalent to the one before. It's a lot of words. I know. You're not really going to get this until you kind of work through it. So I'm going to stop here and let you work through it. There's examples in the text. You can just run through the example in the second half of section 11.3, and this just tells us what the equivalencies are. We know that 0 and 4 are not the same state, so 0 and 4 are individual states, and then we have 1 and 2 are the same, 1 and 3 are the same, and 2 and 3 are the same. Well, that means 1, 2, and 3 are all the same state. So we only have 3 states in this machine: 0, 1, 2, 3, and 4. And we can rename them 0, 1, and 4. We have a new table over here, we have a new table here, and we have a new diagram. So our conclusion is that this diagram here, this state machine represented by this set of states and transitions, is equivalent to this state down here. We're going to call this the minimal state graph. It's a bit daring for us to call it the minimal and just mandate that this process will give us the minimal, but in this case it does. So we'll rest assured that we can call it that. And one of the big takeaways is that the state machines can be written in different ways. And this is more of an application-focused idea in that these state machines are used in compilers, they are used in hardware. Take the architecture class, these things are used all over the place. So state machines are very, very important. And finding a minimal state machine is something that people do. It's cool to see an algorithm because we can program the algorithm. So we know that we don't have to go to Intel or NVIDIA and see a bunch of people by hand running through these processes. But we know that because this by hand process exists, we can now code this up. And given a state machine, given a transition table really, would be the best form, the best data structure to store this table in would be this. We could run through this algorithm and get something that's better. It's not guaranteed to be minimal, but it's guaranteed to be better. And that's pretty good. So it's worth running through this. Again, the takeaway is that you want to spend more time with the concept of state machines. We need to spend more time with the idea of what an automaton is. And by understanding this process, it can help us see that we can have 2 automata that appear to be different in pictures, but are actually the same thing.